This video will discuss a little bit of the kinetic theory of gases, deal with the velocity of gases, the Maxwell-Boltzmann distribution, and talk about phase changes concepts just briefly. So again, the situation, what does create pressure for a gas enclosed in a container? Well, as the gas molecules collide with the walls, there is a force of interaction. Of course, in ideal gas, there's no interaction between the molecules unless we have contact. So at the contact with the wall, the molecule pushes on the wall pushes on the molecule. There's a force present, and this happens over an area. And there are, of course, uncounted trillions and trillions of gas particles hitting the wall constantly, and an average over time gives us an average force on the wall over an area. We create a pressure. The pressure is created by collisions. The force of the molecule on the wall and the force of the wall on the molecule, Newton's third law pair, and they don't add to zero. They act on different objects, and the gas creates a pressure, a force over an area. There are many, many molecules, so statistics are used to create an understanding of what happens in the motion of the particles. As the particles collide with each other, it turns out they create a distribution of speeds. Some molecules traveling at a very slow speed. There is a most probable speed where the greatest number of molecules have that particular speed. And then there's a root mean square speed that's somewhat characteristic and takes into account the fact that this curve is not symmetrical. And we have some molecules traveling at very high speeds. So we calculate the root mean square velocity by taking the square root of a factor of 3 times Boltzmann's constant times the temperature in Kelvin and divide by the mass of one molecule. And this mass of one molecule, you'll have to use Avogadro's number to come up with that value. Certain molecules will have a certain number of grams per mole. For example, nitrogen 14, that particular isotope, there are 2 nitrogens in the molecule, so there'd be 28 grams per mole, just as a rough number. 28 grams per mole, and you divide that by Avogadro's number, roughly 6.02 times 10 to the 23rd, you're going to get a very small number for this mass. But Boltzmann's constant is also a small number. So those two effects somewhat cancel each other. And we end up with root mean square speeds, in this case, about 500 meters per second. And this is oxygen. Notice the temperature here. Do you think this is much different than room temperature? Now, to go back to Celsius, we'd have to subtract 273 from this temperature. Subtracting 273, we get about 27 Celsius. Room temperature is 20, so it's a little warmer than room temperature, but not significantly. This is what's true about oxygen molecules in the room where you are. They're just slightly slower than this, but not significantly. There are some traveling at 1,000 meters per second, and if you recall, to find miles per hour, very roughly, you double the meters per second. So 2,000 miles an hour, so there are some molecules hitting you at that speed. Fortunately, they don't carry much momentum because the oxygen molecule has very low mass. So root mean square velocity, square root of 3 times Boltzmann's constant multiplied by the temperature. Must use Kelvin, don't use Celsius. And then divide by the mass of the molecule in kilograms. I should have mentioned that before, that 28, if I go back here, just this mass of one molecule needs to be in kilograms. When I said 28 grams per mole, that's 28 times 10 to the minus 3 kilograms per mole. Don't forget to convert the grams into kilograms when you calculate the mass of one molecule. This mass needs to be in kilograms. So the common numbers for our molecular weights, oxygen, there we would have 32 grams per mole, but that would be 32 times 10 to the minus 3 kilograms per mole. Enough on that. If we change the velocity, we change the speed. More velocity, and this occurs at higher temperatures. More velocity, there's more kinetic energy. Temperature is a measure of the average kinetic energy in the material. We're not going to go into a lot of the details of the kinetic theory on that. There's some in the reading guide that I provide to my students, but the average kinetic energy is 3/2 times kT. And it's interesting that 3/2, there are 3 degrees of freedom for an ideal gas: motion in the x direction, motion in the y direction, motion in the z direction. And at this point, we're not going to talk about rotation of molecules and vibration of molecules and other forms the energy can take on. But just a simple ideal gas, as we raise the temperature, we raise the average kinetic energy, all of the energy going into motion, either the x, y, z, or directions. On the moon, no atmosphere. We have the distribution of molecular speeds. Some molecules traveling very fast achieve greater than escape velocity from the moon. Earth has more gravity. Earth is able to retain an atmosphere. Then let's get into the subject of what happens as the temperature goes down and our gas approaches the state where it's condensing. We no longer have an ideal gas when this condensation occurs, because now the molecules are interacting with their neighbors. This diagram, pressure and volume diagram, very important for future chapters. We'll discuss it briefly here. But we have lines of constant temperature. These red lines are lines of constant temperature. On the PV diagram, the lower left corner is cold, the upper right corner is hot, higher temperature, and you can see the sequence of temperatures for the different lines that are here. I'd call your attention to this region here. At a certain pressure and volume combination, at a certain temperature, we're going to have a mixture of liquid and vapor. And as this volume decreases, as we condense the material, make the volume smaller, not much happening with pressure. The graph is horizontal here because it's easy to push the molecules in the vapor state closer together. But notice what happens when we get to the left here. Now we're all liquid. In this blue shaded region, there's a mixture of liquid and vapor. But when we get off to the left of that, now it's all liquid. Why does the pressure go up so strongly as we try to decrease the volume? Well, now we're in the realm of a liquid. The liquids are nearly incompressible, so the pressure responds greatly. As we try to reduce the volume of the liquid, the pressure becomes very high. Another thing would be the critical temperature. Above that, we're not going to have a vapor. The vapor has the possibility of going into the liquid state. So enough on that. Phase diagram. Won't emphasize this a lot. Just point out a couple features. First, there's a nonlinear scale on the pressure, so be careful of that. They're just illustrating different, somewhat interesting pressures that occur here. I would call your attention to the 1. That's 1 atmospheric pressure. That's where you exist, 1 atmosphere of pressure. And if the temperature is below 0 Celsius, then we've got a solid. If the temperature goes above 0 Celsius, we've got a liquid. If the temperature goes above 100 degrees Celsius, we have a vapor. And if we go to 374, when we lose the vapor, we get a gas. But this 1 atmosphere of pressure, where we exist, 1 atmosphere of pressure, water has this behavior going from solid to liquid to the vapor state. If we would go to much lower pressures, there is a temperature, 0.01 Celsius, where the solid, liquid, and vapor can coexist, all 3 forms in some glass. All 3 forms would be present: the solid, the liquid, and the vapor. Condensation and vaporization, evaporation, there are molecules leaving the liquid, going into the vapor up here, and there are some molecules in the vapor coming back down to the liquid. Depending on the temperature, this creates a pressure. If the temperature is higher, then more molecules are going to be leaving this material. Again, there's a distribution of speeds for the molecules in the water, and the high-speed molecules will escape and form a vapor up here and increase the pressure in the chamber. Dew forming in the morning. If temperature goes down, the air is less able to hold water vapor, and we get dew forming. If we put water in a sealed tank, there will be an equilibrium established where the number of molecules leaving the liquid and going to the vapor state will eventually become equal to the number of molecules going from the vapor state back into the liquid. They're not showing as many arrows coming back in here, but if it's equilibrium, we'd have equal number of arrows leaving the liquid and coming back into the liquid. There's a certain pressure would be established in the chamber. Bubbles. So if we have room temperature water, put it under a Bunsen burner over here. As the temperature goes up, more of the molecules will leave the liquid state and can go into this bubble region. And at the boiling point, we're going to get a continuous movement of molecules from the liquid state into the vapor state. And that's going to make the bubble expand, and it's lighter than water, it rises. So we get boiling. The bubbles on the bottom being increased in size as more molecules in the vapor state get inside the bubble. They're encouraged to do so because of their speeds. They're able to leave the water state, go into the vapor state. It's traveling at high speed. They're able to break the bonds with the water. And we feed in more particles. The bubble grows in size as it rises. More and more particles come through the boundary of the bubble from the liquid state into a vapor state. The bubble rises. Then carbon dioxide has an interesting temperature and pressure graph. If we lower the temperature of carbon dioxide, and this is happening at room temperature, so here is room pressure, so 1 atmosphere of pressure. As we lower the temperature, notice that this gas, this vapor, does not become solid. We go immediately from the vapor state to the solid state. We have to be at higher pressures for carbon dioxide to act like water. So 8 or 10 atmospheres of pressure, we don't have common experience with that. In that situation, the carbon dioxide would go through a liquid state before it became solid. But carbon dioxide in the environment where we have experience with it, it's called dry ice. It's called dry ice. If we start with ice as solid, 1 atmosphere of pressure, it's cold. As it receives energy from the environment, it warms up. But the solid does not go through liquid. The solid immediately becomes vapor. So dry ice, at room pressures, we don't see the liquid state for carbon dioxide. So there's our tour of kinetic theory and a little bit on phase diagrams. Keep reading and asking questions.